In the last few videos, we discussed various aspects of simple linear regression. In this video and the next, we will discuss key ideas and metrics in multiple linear regression and learn how to interpret the results. We will do a complete end-to-end walkthrough of all these concepts in Microsoft Excel in one of the dedicated videos later on. I'm going to start with the form of multiple linear regression that we saw previously. It's better to use matrix notations in case of multiple linear regression as it's more compact. So here is our OLS estimator. Notice that if we had an exact equation between y and x as y equals to x times beta hat, then we would have solved beta hat as x inverse y. Since we have approximate relationship between y and x, instead of x inverse, we are getting something else. This is called the pseudo-inverse of x. Note that the ordinary inverse can be calculated for square matrices, but our design matrix X did not be a square matrix. However, X transpose X is a square matrix and the inverse exists. So we can calculate pseudo-inverse for rectangular matrices to find solutions for overdetermined systems. Alright, why do we need simple linear regression? One simple answer is that we have other predictors or explanatory variables and we want to know how they influence our response variable y. For example, in simple linear regression, we talked about how the advertising budget on TV drives sales. But we also have the radio and newspaper media, and we want to extend our model to include those variables as well. But why can't we fit three separate simple linear models, one for each media? The first reason is simple. If we are experimenting with the advertising budget on the three media simultaneously, how will we get a single prediction for sales if we have three different models? The second reason is a little bit tricky. The beta coefficients we will get for each regressor in this manner will be misleading. To understand this, first we need to know how to interpret the beta coefficients. In simple linear regression case, say sales is being regressed on TV, beta 1 represents the slope of the fitted line. And so for 1 unit change in the TV budget, the predicted y or the average sales will change by beta 1 times change in TV. In multiple linear regression, the interpretation of beta 1 is change in average sales for 1 unit change in TV budget while keeping all other variables constant. The beta 1 for TV that we get in simple linear regression in general won't be the same as the beta 1 on TV that we get in multiple linear regression. Why is that? The reason is because in simple linear regression, when we change TV, we are not holding other variables constant. And it might so happen that in the data, the TV budget is correlated with, let's say, radio budget. That means when we change the TV budget, it will trigger change in radio budget, which also influences sales. As a result, we get a mixed impact from two sources. One is TV, which we are controlling. The other is radio, that is not part of our model. We call this as omitted variable bias, which basically means that our beta coefficient is now biased because we omitted an explanatory variable from the model. But there is more. Let's understand this visually. Let's consider a simplified two-variable case to understand the scenario that we are talking about. For convenience, let's also drop the intercept term. Now, case 1, x1 and x2 are uncorrelated. Here are the two versions of the models. x1 is included as part of the multiple linear regression in the first one, which is the true population model. In the second one, we only have x1, which is the simple linear regression model, and we have omitted x2 in this model. Now we are talking about the scenario where x1 and x2 are uncorrelated. Now in vector terms, if x1 and x2 are uncorrelated, they will be orthogonal or perpendicular. Now as per the true model, the expected y is a linear combination of x1 and x2 and is given by the diagonal of the rectangle formed by these orthogonal components. In this case, if we do regression of y on only x1, which is the simple linear regression case, then we get the same projection on x1 as we got in the multiple linear regression. Case 2, x1 and x2 are correlated, and our expected y is a linear combination of x1 and x2 and is given by the diagonal of the parallelogram formed by the two components. But here, if we exclude the x2 term, then x1 will be able to explain this much, and the beta 1 is distorted or biased. And we can actually calculate the amount of bias. Part of y that comes from x2 is beta 2 times x2. But since we don't have x2 in the simple linear regression, this part is absent. However, because x1 and x2 are correlated, there is a part of beta 2 times x2 that is carried by x1. And this part is given by the projection of beta 2 times x2 on x1 vector. Now we can find this by regressing x2 on x1. So let's say we regressed x2 on x1 and we found that the projection of x2 on x1 is delta. Now the projection of beta 2 times x2 on x1 will be simply beta 2 times delta, because beta 2 is just a scalar. This part, beta 2 times delta right here, is the amount of bias that gets added to beta 1. So we can write beta 1 in case of simple linear regression is equal to beta 1 of multiple linear regression plus the bias term. We can also derive the same result using statistics. Note that there are two regression models in play here. The one on the left is the true population regression model for y, and it shows how y is related to x1 and x2 in the population. On the right hand side, we have a regression equation for x2, and it shows how x2 is related to x1. If x2 and x1 are correlated, then delta will be non-zero. Now let's take covariance with respect to x1 on both sides for the equation number 1. Notice that the covariance between x1 and u is absent because it's 0, and that's because in the multiple linear regression we are accounting for both x1 and x2 in the model, so u or the error term does not really have anything that has to be correlated with x1. And our standard assumption of error term being uncorrelated with the regressors holds true in this case. Now let's divide by variance of x1. Now we will use the formula for slope coefficient, which is simply the ratio of covariance between dependent and independent variable in the numerator and the variance of the independent variable in the denominator. And we get the same result. Note that when the error term and the regressor are correlated, then in general we get biased coefficients, which is what happened in this case. If we skip x2, then the error term in the simple linear regression, which is epsilon, will contain x2, and so epsilon gets correlated with x1 through x2. And that causes omitted variable bias. Let's understand with an example. This is our advertising dataset. Now let's run 3 separate linear regressions with the variables individually, and then run one multiple linear regression with all variables and compare the results. I will show you how to run linear regressions and produce these statistical outputs in a separate video, but now let's focus on interpreting the results. We also have not spoken about how to calculate the standard error in case of multiple linear regression, and we'll do that shortly. If we compare the beta coefficient of each media under simple linear regression and multiple linear regression, they are not very different for TV and radio, but they are very different for newspaper. In fact, the beta coefficient is close to 0 in multiple linear regression. Moreover, the p-value is significant for newspaper under the simple linear regression, but highly insignificant under the multiple linear regression. What is happening here? The answer lies in the correlation matrix. Note that the newspaper has sizable correlation with the radio, and that's 0.35. This may be because in the data they have spent more on newspaper wherever they have spent more on radio. But since radio is strongly correlated with sales, newspaper gives the vibe that it's a good predictor for sales. In simple linear regression with newspaper gets the credit for the effect of radio on sales. In other words, newspaper's sales are a surrogate for radio sales. Recall that the beta coefficient in multiple linear regression reflects the effect of a predictor on the response variable holding other variables constant. So in multiple linear regression, the contribution of radio is already accounted for, and so if we keep radio fixed, then newspaper has no explanatory power. There is a bit of an exaggerated story to remember this particular theme. Now, number of shark attacks on a beach is found to be correlated with the ice cream sales. Does it mean that we should ban ice cream sales to reduce shark attacks? Of course not. The real reason is that in higher temperatures, more people go to the beach, which leads to more ice cream sales and more shark attacks. Here, the shark attacks plays the role of newspaper in our example, and temperature plays the role of radio. Of course, if we regress ice cream sales with temperature, then shark attacks as a predictor will be insignificant. Now let's talk about goodness of fit. As we discussed in case of simple linear regression, we also use RSE and R-square as the goodness of fit for multiple linear regression as well, with a little bit of twist. First, let's talk about RSE. So here are the population and sample dynamics. For a sample with n observation, y has n-1 degrees of freedom because the mean of y is estimated from the sample. The residual U hat has n values, but not all are free. If you recall, there are k plus 1 constraints on the residuals. So U hat has n minus k minus 1 degrees of freedom. Y hat will have k degrees of freedom, as the total has to add up to n minus 1. Or in another way, consider that there are k plus 1 parameters that has to be estimated, which drive y hat, but there is one constraint on all the beta parameters, that sample average of x and y must satisfy the OLS line. Therefore, RSC is given as square root of SSR over n minus k minus 1, which is the degree of freedom of the residuals. The second measure of goodness of fit is R-square. It's calculated the same way as we did in case of simple linear regression. R-square is defined as the ratio of variance explained by the model and the total variance. Recall that R-square was the square of correlation between x and y in simple linear regression. This is the same as correlation between y and fitted y. In multiple linear regression, this expression holds true as well. In fact, the OLS estimator fits the line in such a way that the correlation between y and y hat is maximum. However, there is a catch. When more variables are added to the model, then the explanatory power increases. Therefore, some of the square residuals, which is the unexplained variance, will decrease. This in turn will increase R-square because SSR falls. Even if we add irrelevant variables such as newspaper in our advertising budget example, then R-square will still go up, giving us a false sense of model improvement. For example, in the dataset that we are using so far, the regression of sales with TV and radio has a R-square of 0.89719. And if we include newspaper, then R-square goes up by a very tiny amount. This is the case of overfitting. Now we will talk about overfitting and regularization in great detail in the upcoming module, but for now, just as a reminder, more the number of parameters in the model, more flexibility the model has, which means better fitting in the training dataset, but poor fitting in the testing dataset. This is called as poor generalization. Also, adding more variables will make the beta coefficients more and more uncertain, which we will see shortly. And from a practical standpoint, adding more variables to the model is costly because you have to source the data, you have to clean the data, etc., which adds to the cost. We never want to add more variables unless we absolutely have to. So R-square must be used with caution. But if we look at RSC, if the number of regressors, which is k, increases, then SSR will fall, which is in the numerator, but the denominator will also fall because k increases. The denominator naturally penalizes addition of more variables. That means RSC will go down only if SSR falls relatively faster than the denominator. In other words, RSC will fall if reduction in SSR more than compensates the penalization effect in the denominator. In our example, RSC in fact increases if we add newspaper to the model, indicating that adding newspaper is not worth it. In that case, how can we still use R-square in a reliable manner? Well, use the penalization term in R-square calculation. So we define adjusted R-square which is more apt in case of multiple linear regression. Alternatively, it can be written in this form as well. The variance calculations will automatically bring these n-1 and n-k-1 terms via their degrees of freedom. Next, let's talk about the variance of the OLS estimator in multiple linear regression. We already know the variance in matrix form, which includes all the individual variances and the covariances between the beta coefficients. For individual variance of beta coefficients, say the jth beta coefficient, we have another useful formula. Now this is directly related to the error variance. It means more the error variance, more is the uncertainty on the beta estimates, which is intuitive and which is what we also had in case of simple linear regression. It is inversely related to SSTJ, which is the total sum of squares for jth regressor. So we simply add the square differences of observed values from their mean for a given regressor j. We also had this in simple linear regression, where we said that sample variance actually helps to reduce uncertainty in beta estimates. Lastly, it's directly related to Rj squared, which is the R square of regressing this jth variable against all other independent variables. It means that if the jth variable is correlated with other variables, then Rj squared will be high, and so the variance of beta j will also be high. We call this multicollinearity, and it's not desirable because it increases the variance on beta estimates, making them unreliable. Consider the extreme case where a regressor is perfectly explained by one or more other regressors, which means Rj square for that regressor will be 1. Then in that case, the variance on beta j becomes infinity and OLS will break. We can also define standard error on beta estimates as the square root of their variance. But we don't observe sigma, we estimate it. So plugging in the estimate for sigma, we get the estimated standard error for the beta coefficient. With the help of this, we can create confidence intervals and perform hypothesis testing as before. But to do that, we need the complete distribution of beta coefficients. The time is right to talk about Gauss-Markov assumptions and discuss the properties of OLS estimator in case of multiple linear regression. The assumptions are more or less the same as in case of the simple linear regression, but there are a few changes. So let's talk about the changes. Assumption 3 is no perfect multicollinearity. We just spoke about this. We know that if a regressor is a perfect linear combination of one or more other regressors, then OLS blows up. Note that perfect multicollinearity is not allowed, while imperfect multicollinearity is still allowed. And practically speaking, we cannot avoid multicollinearity altogether. We will always have some non-zero correlation between the regressors, but it has to be small, because higher the multicollinearity, higher the uncertainty in estimates. Assumption 4 is the zero conditional mean, which now extends to all regressors. Recall that error term must be uncorrelated to all regressors. Assumption 5 is the homoscedasticity assumption, which also extends to all regressors, meaning the unconditional variance of error term is same as the conditional variance of the error term given any regressor. Recall that the assumption 1 to 4 are sufficient to show that OLS is unbiased. Homoscedasticity assumption is needed to derive the variance of OLS estimates and to show that OLS is the best estimator under these assumptions. Normality assumption is only needed to completely specify the distribution of OLS, which in multiple regression case will be a multivariate T distribution. Once the distribution of the parameter estimates is available, then we can create confidence intervals for true parameters and perform hypothesis testing as we did before. Building confidence intervals for parameters is straightforward when we have the complete distribution of the estimator at our disposal. We know that OLS is unbiased under Gauss-Markov assumptions. As the sample size grows large, the distribution of the estimates will approach normal distribution. So for simplicity, let's assume that. Here are the 95% confidence intervals for any beta coefficient beta j. We can also specify confidence regions for parameters jointly. The joint distribution of beta is bivariate normal. For example, if we consider simple linear regression with intercept, which is a special case of multiple linear regression, then we can create confidence region for beta 0 and beta 1 jointly. Notice that the normal and T distributions have elliptical contours. So at a particular elliptical contour, we will be capturing 95% probability, and that will give us the 95% confidence region. Now let's talk about performing hypothesis testing in multiple regression setup. One thing we have been doing is looking at individual t-statistic or p-value and deciding whether a particular predictor is significant or not. For example, in this table, the beta coefficient for newspaper is not significant, and so we do not reject the hypothesis that beta 3 is equal to 0. When we are testing the significance of the variables individually, and if we get p-values of one or more variables very small, then we are happy and we retain those variables. This logic, unfortunately, suffers from a flaw, especially when there are a large number of variables in the model. Why is that? Let's say there are 100 regressors. Since p-value takes a value between 0 and 1, assuming that p-value is a uniform random, there is 5% chance that p-value will be less than 0.05. That means in a model with 100 regressors, you will accidentally find 5 variables for which the beta coefficients are significant purely because of chance. We will get small p-values as a matter of random chance, even if there is absolutely no true association between the regressor and the response variable. And we will end up including those variables in the model. So to overcome this, we must use p-value in conjunction with another test that actually tests the overall significance of the model. This is given by the Fstatistic. Fstatistic jointly tests if more than one beta coefficients are 0. The alternate hypothesis will be that at least one of the beta coefficients is non-zero. Now, how to construct the Fstatistic? Suppose we have k regressors, and let's call this the full model or the unrestricted model. We want to jointly test that the last q beta coefficients are 0. Let's drop these last q regressors, for which we are hypothesizing that the beta coefficients to be 0, and call this the restricted model. So here is the idea. The error variance in the restricted model should definitely be larger than that of the unrestricted model, simply because the number of variables is less in the restricted model. However, if the null hypothesis is true, then dropping these variables should not materially impact the error variance. Therefore, we can test the ratio of the two variances, which we know follows F distribution. Also notice that U has n-k-1 degrees of freedom, whereas epsilon has n-k-1 in parenthesis -1 degrees of freedom, and these degrees of freedom are directly coming from the fact that how many regressors are part of your model. So the numerator has q degrees of freedom, which is the difference between these two degrees of freedoms. So if the p-value for the F statistic is significant, then we reject the null. Also, F statistic does not suffer from the fallacy of the p-value because it accounts for the number of predictors in the calculation. We can also use the F-test to test the significance of the whole model. If the model is good, then at least one beta coefficient on a regressor should be non-zero. So the null hypothesis would be that all beta coefficients for all regressors are 0. The restricted model would only have intercept, which is devoid of any regressor. Recall that SSR for a null model is same as SST. So we get the F statistic for the whole model as this. What if the number of variables used in the model is greater than the number of observations? F statistic cannot be calculated. Not even that, we can't even fit the least square estimation. There would be more unknowns than equations, so there will be infinitely many solutions. In this case, we need to choose a subset of predictors which have strong explanatory power. So the question is, how do we choose important predictors? Ideally, we should try all possible mix of different models. Now we can compare the model performance using suitable model performance measures such as archaic information criterion, Bayesian information criterion, or even adjusted R-square, and then choose the best model that has the best performance. But if there are k regressors, we will be able to create 2 to the power k different subset of regressors or models, which practically is not possible if k is large. Instead, there are 3 different classical approaches that we can use in this regard to select the best predictors. The first approach is called the forward selection. The idea here is to start with the null model, which only has the intercept. The SSR here is the same as SST. Then run separate linear regression with each variable and note down the SSR. Then we choose the variable that results in maximum reduction of the error variance. Let's call it x2. So x2, then run a 2-variable regression with the first variable x2 intact across all remaining variables, and then choose the one that results in maximum reduction in the error variance, and so on. We can choose some other criteria for inclusion, such as maximum increase in adjusted R-square, etc. We can keep doing this until we reach a stopping criteria, such as number of predictors, or desired adjusted R-square, etc. Forward selection is a greedy algorithm, meaning the search for the best set of predictors is performed in a greedy sequential fashion, and whichever variable gets added stays in the model forever, even if they become redundant later on. For example, in this case, x2 will never be dropped from the model. But one good thing about forward selection is that if the number of regressors is large, or let's say even larger than number of observations, in that case we can select a handful of regressors, say 3 or 5, that fits the data reasonably well, and we are done. The second approach is called backward selection. The idea here is to start with the full model, that is with all the regressors, and then look at the p-value of all the regressors and zero in on the p-values which are insignificant, and then discard the one variable which has the highest p-value. So basically the most insignificant one, we discard that. Note that this process is not possible if the number of regressors is larger than the number of observations. We cannot fit a OLS model in that case. So this is one of the drawbacks of backward selection when compared to the forward selection. So anyways, after this step, in the next step, we build another regression model with the help of the remaining k-1 variables. And we follow the same process. We look at the p-values, whichever is the most insignificant one, we discard that. And we keep doing this until we reach a stopping criteria, which could be the fact that all the remaining variables are now significant, so there is nothing to discard. The third approach is called mixed selection. It's basically a combination of forward and backward selection. So we start with a null model, then we add variables using the forward selection method. But before adding the next variable, we check the significance of all variables currently included in the model, and if the p-value of any of the included variables is not significant, then we discard it back to the remaining pool. This step is the backward selection step. So let's say that x3 and x4 are currently included in the model. Now let's say x7 got added via the forward selection step. And x3, which was already included, became insignificant, so it will be discarded as part of the backward selection step. And so on, until we reach some stopping criteria. Mixed selection is not a greedy approach because variables that were added earlier can also be dropped later on. So that's how it is actually superior to the previous two methods. As we wrap up, let's spend some time talking about the distinction between confidence intervals and prediction intervals. For convenience, let's assume that we have 3 points in our sample and we fitted a OLS line which is different from the true population line, and we don't observe the true population line. Now for a given x outside our sample, the true population average y is given by f of x, which we don't know. And we get an estimate for it, which is y hat, from our fitted line. Now we can create a confidence interval for the true population average of y, which will be centered around our estimate. Now to build this confidence interval for the true y, we need the variance of y hat. So let's derive it in matrix notations so it can be applicable for regression in general. So y hat is x times beta hat. Then we take variance. Notice that x here is actually fixed. We are talking about the fixed sample. The randomness is coming from the uncertainty in the parameter estimate, beta hat. So we obtain the standard error as the square root, and assuming normality, we can create the confidence interval for average y, true average y, given x as this. So we got the confidence interval for average y centered around our estimate. This error between the estimate of average y and the true average y is reducible if we use a low bias and a low variance estimator. However, we are interested in predicting the actual y, not the average y. The actual y for any test subject will be the average y plus the error term u specific to that test subject. We don't observe u, neither we have any way of predicting u, and u will also be different for different test subjects with the same x. That's why u is called non-reducible error. Our prediction interval in which the actual y should lie will even be wider because it includes u. To calculate the prediction error E, we write error equals to y minus y hat, because y hat is our prediction whereas the actual y is something else. Now replace y with f of x plus u. Notice that f of x is unknown but fixed. Taking variance on both sides, we get this expression. Notice that there is no covariance between u and y hat because u is the error term of an out-of-sample test subject, whereas the variance in y hat comes from the in-sample error terms. So they are not correlated. And we get this expression. So using this standard error, which you can see is a little bit bigger than the confidence interval standard term. So using this, we can create our prediction interval for y. Notice that the previous one was the confidence interval for average y based on our estimate. This is the prediction interval for the actual y, which includes the idiosyncratic error that we really don't control. That's all for now. Thanks for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peakstotales.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.